In this video, we'll take a look at our new piano synthesizer, which is designed to work with the Harmonix plugin on Unreal 5.4. Piano is a complicated instrument, so building a physical model for it isn't a simple task. Then we also have to make sure it works properly with MIDI standards and the Harmonix API. Thus, it took us 3 months to finish. With this new update, you will need to enable Harmonix plugin in your project. Even though it's marked as experimental, it's very stable. After testing with hundreds of weird MIDI files from the internet, I didn't have any crashes. If your MIDI files contain some weird stuff in them, Harmonix won't be able to import them properly. For those files, you can import them into a digital audio workstation software and then export them to MIDI again. And Harmonix will be able to import them into Unreal. You will also see these 2 error messages on startup. Avoid this node and you will be fine. They won't cause any issues when packaging your project. The most important node that we need from Harmonix is the MIDI player node. I will set MIDI to Moonlight. You can view MIDI download link in the video description. This transport is a collection of triggers. You will need to break it out like this. And connect on play-to-play trigger. We do not support pause trigger at the moment. Also note that Harmonix doesn't send a MIDI end message, so there is no on-stop trigger. These might change when Harmonix is out of the experimental phase. This is all we need to set up this MIDI player node. Now, I will connect the MIDI stream output to our piano synthesizer MIDI stream input. By the way, this MIDI stream also includes MIDI clock in it, so you won't see MIDI clock input here. Then, you will need to select the track to be played. Track 0 is usually used for some global settings instead of MIDI notes. So by default, we start with track 1. All the MIDI files I will play today only have piano in them. So I will just set this to -1 to let this node play all tracks. Currently, we only have one piano model for a grand piano. It's modeled after a Steinway grand piano. We have 3 quality variations for this grand piano model. High quality and medium quality are what you're going to use the most. Low quality is meant to be used on mobiles. Generally, the higher the quality, the more harmonic and enharmonic frequencies, aka our overtones, a note will have. If you open these files, you will see how they are created. Currently, we do not have many customization options. But in later updates, we will allow you to customize velocity, gain, and pitch per key by using curves. It will be kind of similar to the residual data editor. Now you can press play and listen to the output. The dynamic range of classical pieces can be really large, so I will increase the gain to 2 to make quiet passages louder. And listen to it again. Now, what is the difference between velocity scale and gain? I will change the gain back to 1. Then increase the velocity scale to 2. And listen to it again. By changing velocity, not only do all notes sound louder, they also sound brighter. This is because on a real physical piano, playing a note at different velocities will also affect its overtones. If I reduce the velocity scale, they will sound softer and darker. Changing the velocity scale and play speed will affect the mood of a piece. Note that, by MIDI standards, the maximum velocity is clamped at 127. So if you increase this too high, all notes might be played at the same velocity. So, in short, if you simply want the MIDI to sound louder, increase the gain. Only change velocity if you also want to change the overtones. Key gain or harmonic gain allows you to only change the loudness of notes or hammer noises respectively, though you rarely need to use them. To understand sympathetic resonance, I will change the MIDI input to sympathetic test. Let's take a look at this file first. Note G5 is played 2 times, so you can compare it before and after C4 is played. Note C4 is played and kept pressing down even if its strings have stopped vibrating. As long as the key is pressed, the damper of C4 isn't returned, so its strings can still vibrate again. Because G5 overtones also have some of C4 overtones, C4 strings will resonate with G5 strings when note G5 is played. Let me increase the gain so you can hear it easier. Even though the second G5 note has the same duration as the first one, its tail is much longer. This is due to C4 strings keep vibrating because of the sympathetic resonance effect. This is a subtle effect, but it plays an important role when playing chords. Compared to a sample-based approach like Fusion Sampler, a physical modeling approach like this can simulate this effect easier. Most commercial sample-based VSTs and mid-range digital pianos don't support this effect because it can be quite CPU intensive. By adjusting the dynamic range, you make the quiet parts sound louder and the loud parts sound softer. This is very important for music, especially when you need to mix this with other instruments. Traditionally, you can use a compressor to limit the dynamic range. But in real-time applications like gains, compressors can be quite expensive. Thus, we also provide a built-in dynamic range adjustment solution for this node. Its calculation is based on our physical model, so it's lightweight and quite accurate. If you set this to 0, it's disabled. Let's test this with another piece. The dynamic range is very large. If we simply reduce the gain, then the other parts will sound too quiet. So by default, we enable dynamic range adjustment to 1. Let's test this again. All these gain and velocity scales are included in dynamic range adjustment, so you can increase them without worrying about the output exceeding -1 and 1 range. Soundboard gain is not, so we leave it below the dynamic adjustment input. The soundboard is synthesized similarly to how the reverb system works, so it's harder to predict the output. If you increase the soundboard gain to be higher than 1, the output might exceed the -1 and 1 range. So always preview your output carefully if you increase the soundboard gain. Or you can also further reduce the dynamic range to avoid problems. The soundboard has a quality scale setting. 1 is the highest quality, and 4 is the lowest quality. By default, 2 is actually what we will use most of the time. By the way, if you reduce this gain to 0, then the soundboard calculation is skipped. This will reduce CPU and memory costs, but also make the output less realistic. That's all you need to know about the synthesizer. If you want to transpose your MIDI, you can use Harmonix nodes like this. You can also filter out piano tracks and play them like this. Let's see this file first. It's a MIDI for jazz. Piano tracks are 7 and 8. This node supports sustain and sostenuto pedals. For soft pedal, you can implement it through a CC triger node like this. Then you can decide how the gain will be changed. On a real piano, a soft pedal will also shift the pitch slightly. You can use the MetaSounds pitch shift node for that. Now let's compare our synthesizer to Fusion Sampler. It isn't a fair comparison because Fusion Sampler is a generic solution for all virtual instruments, so it isn't really optimized for just one specific instrument. You can find some sample presets in the Harmonix plugin content folder. Since they are just examples, they are very simple. For example, this piano preset only has one sample for several keys and covers all velocities. A real preset will have around 3 to 5 samples at different velocities for one key. That means an 88-key piano with 5 velocity layers will need around 440 samples. Also, the sample here is only around several seconds, but a real one might need around 35 to 15 seconds, depending on the node. Fusion Sampler doesn't support pedals. If it does, you can improve the quality by adding samples when the sustain pedal is pressed. This is why even a mid-range piano sampler needs several gigabytes of storage. On the other hand, a physical modeling approach only requires several hundreds of kilobytes. Now let's compare the performance. Because it doesn't support pedals, Fusion Sampler isn't really good for tracks that require them. If you look at CPU load, you can see that at some parts of the piece, our costs are similar. But when the sustain pedal is pressed, we will have more CPU load. This is because the sustain pedal prevents dampers from returning to all strings. So we have more concurrent playing notes than Fusion Sampler on sustain parts. Well, this is the composer's intention, so there is no way around this. And that is all you need to know about our new synthesizer. If there are no other problems, we will release the new update on the store next week. For future updates, we will add customization options for piano models, as mentioned earlier. Then we will return to sound effects. Currently, most of our SFX synthesizers rely on modal objects. In the future, we want to add more synthesizers that take an audio stream as input, and output something new or an enhanced version of it. This will give you more flexibility and control over your SFX chain. Bye for now, and I'll see you again once another update is ready.